let's look at problem 990 again. So satisfiability of equality equations. In a previous video, we provide a unified solution, and here we would like to also share the traversal solution, either breadth first search or depth first search. So first I'll go over the statement of the problem quickly, then we will explain the idea, and finally we give a simple implementation. The statement is as follows. So we are given an array of strings called equations that represent relationships between variables, and the equations can take two different forms, either a equality relation or an inequality relation. Here xi and yi are the variables involved. They are all lowercase letters. So we are required to return true if these equations are consistent. Otherwise, we are required to return false. So the constraint, roughly speaking, is that the equation is not empty and has length up to 500, and the variables involved are lowercase English letters. Again, the two examples give a inconsistency example and a consistent example. So in this video, we are going to provide a solution using traversal, graph traversal, either breadth first search or depth first search. So actually this method, if we think a little bit deeper, they are sort of the same as the unified method. So ideas are parallel. So the idea are as follows. First, we use equal relations to construct a graph, and then all the equal variables form a connected component. Secondly, for the inequality relations, we are going to check the root for if the two variables reside in the same connected component. If so, there is inconsistency. So let's look at one example to fix the idea. For example, if we currently have this equations list, then due to the equal relations, there are two components formed. One is ABC from the first two relations, and the other is EFG from the last two equations. So if we want to add A does not equals to C to the list, then this will induce inconsistency because A and C are actually in the same component due to equal relations. Similarly, A does not equal to E. If we want to add this one into the list here, then it's okay because A and E are actually belonging to different components due to equal relations. So with that said, let's also remark that we can use similar method and modifications to give a solution to problem 2307, or you can also see a previous video for the unified method for this problem. So now let's implement the breadth first search or depth first search here. Again, we are going to put this implementation into different steps. First, step 1 is make some preparations. For this, I'm going to first initialize an empty graph and a checklist. So for this, we are going to graph is I'll call some libraries, collections, default, dict. I'm using the container as set, and then also we will have a check variable to record the inequality relations. So first I want to construct a graph. So the graph will be bidirectional. For this purpose, let's iterate in the equations. Again, let's see, for equation in equations, I'm going to check if this equation, the first or three element is equal or not equal. If it's not equal, I'm going to track AB like this, split, and we split at this symbol, right? So we will add this tuple to the checklist due to its nature. It's not equality, right? So we will check add this AB. Otherwise, we're going to get AB like this. We split from the equality sign, and then we are going to update the graph. So the graph A, I'm going to add B, and in graph B, I'm going to add A. So this actually is a node and the list representation of the graph. So with that done, basically we have done two things. First is that we have the check set for inequality relations here, and also from the equality relations we build a graph. So now let's look at step 3. So step 3 basically is a DFS or BFS helper function. So for this, basically each method, BFS or DF, will do, because they are both valid to get the connected component. I will first implement a breadth first search method here. So we get a start character and we get a target character. So the start and target we're going to check is from the checklist. For this, I'm going to initialize a queue, because if we want to implement breadth first search, the corresponding container to help is a queue. Or if we want to use depth first search, the container will be stack. So let's, here for convenience, I'll make a collection call, but it's not necessary. So I'll call this queue and start with the U, the start node. So we initialize a dataset called visited to track the nodes we have already visited. Then we do the iteration while queue. Well, this loop is not empty, so we're not going to pop this one. So we're going to pop queue pop left. So this, we regard the left as the head and the end as the tail. So we first check if this U equals the target. If so, we're going to return true. Otherwise, if U not in visited, I'm going to update visited by adding this U, and then we check the neighbor of this U. So for V in graph U, graph U means the neighbor side of the node V. Then we check if V not in visited. So then we're going to append this new node to the queue. Append V. Finally, if we haven't returned anything, we're going to return false. So this breadth first search basically check if U and target are in the same component or not. So here we are using pop left. If we use pop and we pop from the tail, then the function will correspond to a depth first search solution or function. So with that done, we are ready to do the last step. The actual work again is to check for the inequality relations if they are in the same connected component. If so, there is inconsistency. Otherwise, it's okay. So we are going to, for A, B, UV in check. So we are going to check BFS, U and V. So if they are in the same component, then they are seeing that UV should be equal, but we are starting from inequality relations, so we're going to return false. due to the inconsistency. So after the for loop, if nothing returns, we're going to return true. So that's a simple implementation for this one. Let's overview the structure. First, we make preparations in order to write the DFS function and construct the graph. Secondly, we construct the graph, and thirdly, we do the hyperfunction implementation, and lastly, we do the actual work. So now let's have a check for the special cases. So BFS, let me update this one. Name UV. So let's write this as AB. Yeah, this passes the generic case, and actually let's try the examples cases here. So this should return false. And let's do this. This return true if we have two identical ones. So let's check generic case again. Yeah, it passes the generic case. For this problem, I guess that's about it. Thank you.